The new ones, I hope they don't kill off
They kept hinting that they will, and then they finally released the teaser now, where they like dig them out of the rubble and just tell them like that.
Okay, so we are going to study a few slides of Chapter-5. Then more to the lab, which is acid-base titration. Right.
He doesn't need anything. Come on.
Yeah,
So in Chapter-5 we study gases. Chapter-5, I think did I give you back? Yeah, for 1 and 3. So we'll start on the beginning one. You get the schedule for 1 and 3? So in Chapter-5 we studied the gases. We talk about to this class. Gases in reality is similar, but sometimes if the pressure is high, the temperature is low, and so there will be some of those attraction between those gas particles. But in this chapter, we mainly use one assumption. We are assuming the attraction between gas particles is very weak, and those gas, there are only a few particles in the gas. So therefore, we think about they don't take any rooms away, right? So we use that few variables to study gas, and we say we have that variable pressure is P, and volume is V, and the temperature is T. Now, how much gas do we have? We call that N. Right? So we have these 4 variables, common 4 variables to describe gases, and so you know sometimes you have to know like what unit you use for each of those variables. So usually those depend on the law. We said we have two different type of law. So those units depend on that 2 types of law. There are 2 types of law. One type we call them individuals. Individual law, and there are 3 we are going to study. In reality, more than 3. So the first one is Boyle's. The second one is Charles. And the number 3 is Avogadro's. So then the other type of law is ideal gas law. So depending on what law we use, then we have to worry about what unit we should use for these 4 variables. So to summarize, no matter what law you use, one variable has a unit, you know for sure always use that unit. So if for both laws, the T will be in Kelvin. So then beside this T, there is a pressure, volume, and N. So in this individual, if I put this, if I draw a line here, in the individuals, P, V, and N, any units, put in the quotation mark, any, that means you have to make sure you be consistent. So if you want to use, for example, you want to use milliliter for the volume, make sure you just use milliliter volume for all the volume. If you want to use pressure like a millimeter mercury, mmHg for pressure, then make sure you just keep use that unit. So then for the second one, for the second law, you memorize that depend on the R. Okay? So if we see R is the gas law constant, and constant is constant relatively speaking because depending on unit you will have different numbers. So one common unit you use for this R is, let's see, we let R equals 0.08206. You can use some other unit, you can use some other numbers, but you will have a different unit for all those pressure, volume, and N. Okay? So you will memorize one value for R, and so then this number will specify the pressure will be in ATM. Right? So in that first type, those Boyles, Charles, Avogadros, if you need to use pressure, you can use any unit. You can use PSI, you can use inch mercury, as long as you use them in the whole program like consistent. Right? But once you use the ideal gas law, by the way, the ideal gas law has this equation PV equals N, R, and T. So that means you put all those individuals together, get this. Right? And so then there's R here, R is so-called the gas law constant, and you have to memorize the number for the constant. Usually use 0.08206. If you use that, that means your pressure cannot be some other unit, should be ATM. And then your volume cannot be milliliters, should be liters. Right? And then your temperature still in kelvins. And as I said, for both these two sets of laws, the two type of law, use the temperature, make sure you don't use Fahrenheit, you don't use Celsius, you have to convert into kelvins, or very simple, it's adding 2073. And the N should be in mole. Right? So that is about the unit. Then you think about how do I find out which type of law do I use? How do I know I use the Boyle's law? How do I know I use the ideal gas law? So we talk about that Tuesday's class. So for this law, and then those individual's law, so this ideal gas law, this individual's law. Individual's law has two sets of conditions, and both of them, talk about that four variables P, V, N, and T. So when you have those two temperature, maybe two volume, and so then you think about this belong to those individuals. And if you only have one set, one temperature, one pressure, one volume, and you want to find out what is N, use this one. So therefore this has one set of condition, right? So that's it's kind of like a rough guiding line to to help you to figure out which law should you use. If you have two sets, two temperature, and two volume, you think about use Charles' law, and Charles' law I'm going to study pretty soon is the individual. If you are given two pressure and give you a volume, and then you want to find out what is the other volume, so therefore you have two pressure, two volume. That's what we studied Tuesday, the Boyle's law. So that in Boyle's law, or in Charles' law, or the Avogadro's law, make sure just if you have temperature in the equation, the temperature T should be in Kelvin, all the others in any unit. You will have like pressure 1 and pressure 2. Just make sure if you choose pressure 1 is PSI, then pressure 2 should be PSI. Alright, so that is a quick summary. So I think about either I give you this summary before I talk about this law, or after I talk about this law. So either way. Alright, so now we already studied one of those individuals, so that the Boyles, we are going to study 3 of that. And So the first is the boils. So the second one will be the chars. Which one is first, which one is second, doesn't matter. So all those laws again we said is about these four vertebrates, and those these three individuals, boils, chars, and avogadros, only has so each of those laws only have two vertebrae that's innate, two vertebrae, and you have four vertebrae here. So therefore, you control the other two as a constant. So in boils, you control the temperature and N as constant. In chars, you will control the pressure and N as constant. Because as you will see pretty soon, and so you find out, from that chars, the first experiment, he found out the volume called the weight equals constant times t. And that constant is a constant, just something that's constant. Usually will be not the same as this constant. Right, so that tells you that volume is directly proportional to the temperature T in Kelvin precisely. And it can also be proportional to that temperature in Celsius in Kelvin, but not that proportional, not that good, because that will not go through the zeros. So that tells you if it's directly proportional to temperature, so that means if temperature T increases from this equation, you can really see that very easy. If T increases, constant or not change, if you keep that pressure, keep that N constant, and then volume will increases if the T increases. Right? Right. So you can study from these concepts and write up different equations. So I would suggest you just try to memorize one way of writing the equation, and don't bother about somebody else use some other way. Because each equation you can write in a different way. So we will compare what we write for the boils. For the boils, remember we write P1 times V1 equals P2 times V2. We pretty much will keep this habit. We write condition 1 on one side, condition 2 on the other side. And here the volume and temperature, 1 and 1 on one side, and 2 and 2 on the other side, and you have this equation. Right. So once you have those equations in memory, and if you use what I talk about here, if you see the problem, give you one set of those variables, and use this ideal gas law. If it gives you two sets, maybe two temperature, and one volume, want to find out the second volume, so therefore, once you find out the second volume altogether, you have two temperature, two volume, and belong to these two sets. You think about use those individuals. Alright, this is very easy, and so then you can also understand that Charles' law, like from those molecular viewpoint. So remember what we studied in this class, you study chemistry by studying the behavior of molecular atom or ion, because those are the something we cannot see really with our naked eye. But if you try to try to reason in those behavior or those law from those kind of behavior, and it makes sense. Okay? So how do we understand that the Charles' law? Charles' law tells you the volume is directly proportional to the temperature in Kelvins. And you can see these two pictures. We have this gas examples. In this gas example, in both of the gas examples, we see we probably will start with this left side picture. So forget about this one first. So therefore, we have that certain amount. How much gas we have inside the container. And both of these two pictures is about at the air pressures and atmospheric pressure, not really in some like condenser or something, right? So you compare this at ice water and boil water, and therefore we keep the pressure P constant because both of them exposed to the air, and we keep how much gas we have inside are the same, even though this looks like it has more, but actually this has the same amount. Right? So then why at lower temperature the volume is smaller, at high temperature the volume is larger? That is because if you keep the external pressure constant, so in both of these two pictures, in both the lower temperature or high temperature, the external pressure, so something like the pressure here, that push on this balloon, let's call that P air, and here it is also called the P air. So in both of the P air, that the squeeze the balloon are the same because we are assuming we did not change the pressure of these two conditions. And so then this looks like it has more pressure. This is going to explode in the pop, but that has more pressures. Actually, they don't have more pressure. They have the same pressure. You keep the external pressure the same. And why this has like a lot of volume, that has lower volume? Because in order to keep the pressure, keep the inside pressure, if you put it here, so this will be our P gas, and this will be our P gas. So the P gas and the P air should be the same. And in order to keep this P gas equal to the P air in this at high temperature, the gas particles are moving faster. So when they move faster, when they strike on the surface, they will carry more force. And the pressure will depend on how much each particle gives you the force, and also depend on how much particle give you the force. So you have to dilute the gas with high temperature, so make sure there is less gas strike on the surface. So even though there is more force from one gas particle, but if you make the volume larger, so the number of gas particles will strike on the surface getting less. So therefore the total pressure are the same. Alright, so that's about how you're understanding those laws. Right, and you also can understand those numbers by use those mathematical graphing or equations. So if you do like some of those tests, and I don't know why my right, so this lagging somehow sound like something wrong. So I just tell you those different color line, and representing different gas and different amounts. But once you do the lab, you keep that pressure constant. And for one gas experiment, if you start with 2 mole of oxygen gas, you keep that 2 mole inside, just change the temperature, and then you measure the volume. You have this one line. For another gas, you might not take exactly 2 mole, you might take 3 mole. But when you have 3 moles, keep that constant, and then you just expose to the air pressures, change the temperature, get another set of experiment. Right? So you can see there's 1 gram and 1 gram, then maybe like different gram of gas. Right? So what is important for this graph will tell you, if you have this temperature, that is the volume, and if you use the temperature like in like as one axis, you use the volume as another axis, and you do the graphing, you can see within the experimental areas, pretty much all the gas under that condition, pressure is constant, number is constant, you have those straight line. So then you can obviously keep the temperature lower and lower, then your volume getting lower and lower, but depend on technique, and so you have those data, then you do like those extensions. And then all the line, maybe they have different slope, but once you extending the line like to lower temperature, and then they all like condense, they all like convert into the same point. At that point, that reduced volume becomes 0, and the temperature becomes negative 273.15 Celsius. Obviously, that is not true because. As I said, unless that is really good ideal gas, any gas, you condense them into liquid, and when the temperature is getting low, they will even become like a gas, become solid. So therefore, you will have some volume. That volume becomes 0 is not really something you can achieve. So therefore, that temperature you cannot achieve. But we define that as a reference point called the absolute 0 times the scale called negative 273.15 Celsius. Right? So those probably don't matter, and what you want to study for is I give you some programs, as I said, you identify which law you're going to use and how to use that, what unit to use. Right? So this example is a example of gas has a volume of, so give you one volume, and then tell you a temperature that you don't know, and so this is the way, and this is T, and then tell you another T here, so another T here, another way here. So you can see they give you two volumes. And if you solve the problem, you will see how you have two temperatures. So therefore I said those are the so-called two sets of conditions. So you think about the law, either the Boyle's or the Charles. Just memorize what the Charles about, what the Boyle's about. So when you have the temperature constants, the N constant, you talk about the pressure with volume, use Boyle's. And when you keep that pressure constant and the N constant, and you are going to use the Charles. So just remember Charles' law has that equation, has that format. So T1 over V1 equals T2 over V2. There are many different ways to write the equation. You can flip that around. You can write like V1 over T1 equals V2 over T2. So I choose going to use this format because I know we are going to find out one temperature. So you put the temperature on the top, it's not easy to solve the problem. So once you decide you're going to use the Charles law, so little details, you keep that. I choose the first, I search out because I said you're going to find the temperature. If you want to find temperature like T1 or T2, you multiply the V1 over, and that's just one step. Alright, so then the second is you want to identify what to pair with what. So if I call this first is our V1, and then that tells you that at that volume you have an unknown temperature, so this will become T1. And so if that is V1, you have another volume, so this will be the V2. And then this volume that appears at this temperature, so this temperature will be our T2. So very easy. And so then you just solve statistics. You can solve statistics like what do you find out? And let's say we have that T1 we don't know, so we just put T1 here. And then V1 we set it to 280 L. Then that equals, let's say, T2. And so remember what I said here on one slide. I said so those temperatures from always in kelvins, right? And the individual law, those volume, what the unit doesn't matter. In this case, if liter is good. If ml is also good. If gallon is also good. Now the other temperature is T2. So in this initial problem give you T2 in Celsius. So before you really put into the equations, or you can just put something like that. So I will just write 273.15 plus 0. So like that because I want to change so make sure in the calculations your temperature in kelvins. Right. So no matter how much I emphasize, you should like memorize that. And so now what is our V2? So V2 will be 257 L. Right. So as I said, so that's very easy to solve if you choose this right formula. Because otherwise I do the cross multiply and then divide and so on. Right. So you can see here you have the T1. You want to find out right now on the top. So you want to get a bit of this number. You just multiply 280 L on both sides, and you will get. So that's it. This is one step. I will multiply T1 here by 280 L and then 280 L here. Then you do the same. So this becomes 273 kelvins and 257 L. Well, anyhow, you know what I want you to do. That's L here. So more than 10 not sometimes not work as good. So T1 times 280 L and 280 L equals. So initially we have that T2 is 273 kelvins now, and we have a 2.57 L. So I also want to multiply 2.80 L here. Alright, so let me start with something here. So this is I just usually put on compare with what we have here. This is not that clear, right? Understand? Okay, forget about those. So what I did here is take that equation and multiply 2.80 liters, 2.80 on both sides, and that is the typical way to solve the chemical, solve the mathematical equations. Yeah. So now once you have this, you are just cross and cross. Yeah. That's why I said you can save one step. You don't have to do a cross. You don't have to do a cross. Okay? Do a cross will cost you one more step. You cross this one, and then you have to divide. Okay? So there's just probably that's the same. But if I see that there's I forget my name. So this is one. Right. So then you just see this error and error comes out. You get 280 divided by 257 times that, you get only unit that row is a Kelvin. Right, so you get a Kelvin. So sometimes you have to convert into the Celsius back. So 280 divided by 257 times 273. Right, so you get 297 Kelvins. Understand? So we go through the temperature in all the calculations with gas using Kelvins. Even though you get Kelvins, the multiple choice answer might ask you again change into Celsius. So what you do just you will get Celsius minus 273, and you will get 24, about 24 Celsius. All right, so that is one example. Now you do a practice, okay? Do a practice. First identify what kind of equation should you use. Even though we did not study the ideal gas law yet, okay? So because you understand why you use some law. Which law shall we use? Boyle's or Charles? Charles. Yeah. So even though this also gives you pressure, right? But then tell you that the pressure will keep constant. And so if you keep the pressure constant, and if you keep the N constant, and the only other two variables that is not constant, don't vary or change, is volume and temperature. Okay. So then once you decide the Charles law, think about the equation for Charles law. What's the answer?
A.
Very good. Yeah. Okay, so that's, I think this parameter, that's why I emphasized those at the beginning. It's easier to do the calculation, it's difficult to know like which one to use. Okay? And also like think about the unit. Okay? Right. So this pressure doesn't matter because you keep the pressure, keeping the pressure and the amount constant. Okay? So you're going to use the Charles. Okay? So you can write, let's see, what do you want to find out? You want to find out the volume, right? So the last one you want to find the temperature. Now this one you want to find the volume. So what you write, you just write the volume on the top. Because if the volume on top, and just multiply that whatever temperature you just get the answer right away.
No, temperature.
Right? So remember that equation I write there, see the T on top? Now you can write it different way. So I'm going to write that on V on the top. So I'll write V1 over T1 equals V2 over T2. Alright, so you can write either on the top. Right? So this is the same. And so then let's see which one I'm going to call that T1, which one call that T2. Just identify, we could write association. So I think this is one set, right? So this is the first set of conditions. So that tells you at 1 atm, at this amount of temperature, your volume is 0.65 liters. So if I call this our T1, and this one will be must be our V1. That must be V1. Right? You can call that a V2 T2, but as long as you call them the same number. And so then this is another temperature. Right? And this temperature will be what? Or T2. And this volume, calculate this volume. Now this volume will be what? Or V2. So V2. Right, so then just substitute. So do we know V1? Yeah, so 0.65 L. Do we know T1 in Kelvin? Yeah, if not in Kelvin, in one step, just adding on 27 right? So that's good. So you have 305 Kelvin. Do we know V2? We don't know V2. So if we don't know, just keep that as a variable. Do we know T2? So 77 Kelvins. You know all the steps. And so now you want to find out V2, right? So V2 right now on this side, not matter on the right side, on the left side. You want to get this by yourself, you just get this out, right? So if on the top, you can see one step. Right? You just multiply 77 K here, multiply 77 K here. Right? I put this in the parentheses, okay, because that is the step we just what we did. Understand? Right? So then you say this is all crossed out. It's all crossed out, and that's much easy. And then this K and K come out. Yeah, so then you do a calculation, you will get some number that will be smaller than 0.65. That makes sense because the charts will tell you the volume is directly proportional to the temperature. Right? If your temperature go from 305 Kelvin and decrease to 77 Kelvin, that is a very, very low temperature. About negative 200 Celsius. Alright? So you do a calculation of V2 become 0.16 L. Alright, any questions? So you are okay. So you know like how to study this class now, okay? So if you feel like you need to put more time, just put more time. More practice and you are more fluent. Chemistry is kind of another language. Right. So we studied 3 of those laws. Okay, the Boyle's is our first we studied, then Charles, and this Avogadro's. Okay, so in Avogadro's, possibly you still have that 4 variables. Okay, in the Avogadro's, you're going to keep this pressure constant. You're going to keep the temperature constant. So then what else can change? Probably the volume and N. Right? And so then this Avogadro, you see the Avogadro number named after him is because he's the first one who studied those gases really in details. He found out equal volume of gases contain equal number of molecules. So therefore, how many molecules we have in one mole, so we name after him. Not really, he found out that number. So that tells you like this kind of proportional, the volume, when you keep the temperature pressure constant, the volume of the gas is directly proportional to the N. If N increases, your volume increases, which makes sense. If you put more gas in, for example, in the balloon, and if you keep that pressure temperature constant, your balloon volume gets larger. Right, so let's see the equation. The equation again, as I said, I will keep the similar format. So I will write, because we have two sets, we call that 1 and 2. So we will write that one set on one side, and the other set on the other side. And so then you have this format. And this format, you can change it. You can write the n on the top. You can it's very equivalent. You can write something like this. So both equations are the same. You can even cross multiply to some other format. But as this, you have these two, and that's very good, because if you want to find out n, you use this. If you want to find out w, you use that, because you will save some step. Right? Right, so let's see, do some of these examples. So I tell you this Avogadro's law, so then you know you have Avogadro's law. Otherwise, just exam how many volume gives you, how many temperature gives you. And so then once you know that, you just worry about that unit, and you don't have to worry about too much unit, just the temperature. Right? So 4.65 liters sample of helium gas has this matter, has 0.225 mole of helium. How many additional mole of helium gas must we add to the sample to obtain a volume of 6.48 liters, assuming constant temperature and pressure? That is the perfect condition for the Avogadro's law. Right? And it makes sense too, because you can see you start with 4.65 liters of gas and keep the temperature and pressure constant, and you want to increase the volume into 6.48 liters, and obviously that makes sense, makes common sense. You want to add more gas. So then the question is, you want to add in gas, but in the Avogadro's numbers, you add the gas you add on with the gas initially you have, you don't know the difference. So therefore, the Avogadro's law, probably the first step, you just find out what is the mole for this 6.48 liter, and then compare that mole with the initial mole. You find out how much do you need to add. Right? So we want to find out the mole. So therefore, I will write that equation. Remember, we can have two equations, right? I will write that n on the top. So I write n1 over v1 equals n2 over v2. Alright, so then you will assign those numbers. So if I call this in our, so this is one volume, so I'll call this in our one volume, this is the n, so I'll call 1n. And you will see this together, well, you see like this amount of number contains this, so therefore this is together, so we'll call this is, maybe call this is v1, and this will be our n1. Alright? So you have two volumes, there's another volume, right? And if you already have a V1, so this must be our V2. It's very, very straightforward, very simple. And then the next step, just substitute, put all those numbers in, and you have V1, so 0.225 more, and then you have 4.65 L, so right here, and then you have that N2 you don't know, right? But then no other moles, no other information. And so then you have V2 6.48 L. So I choose the N, so whatever you want to find out, just write that on the top. And the second thing to remember, 1 always on one side, 2 also on the other side. And then you just multiply this 6.48 out, you get N2 right away. So you're going to skip one step now, just write 6.48 L times 0.225 more and 4.65 L. I like to put them in the parentheses, because putting the parentheses will tell you more like easy to say, this parentheses means multiply. And also like in the calculators, sometimes you do those kind of calculations, and that will make sure you have that number you divide, so you divide all those numbers. And this is our N2. Right? Since this L and L come out, right? So you get this N2. So for this question, when you get N2, it's not really the final answer, because N2 means how much more you have for this 6.48 liter, right? So 6.48 divided by 4.65 times 0.225, you get 0.314 more equals N2. Just read the question carefully. I hope you do the same, read the question carefully like for today's exam. So those questions sometimes give you the answers, maybe you will see the answer, but not really the right answer. So this N2, and this is N2 for how much more you have for this volume. Okay? Now this volume, is pair up with this much more, but this much more it means you have the initial more in it. So what you want to find out is you'll find out how much do you need to add on, right? And how you find out how much do you want to add on? Initially you have some more in it. And that much more is this much more. So you have 0.225 more, and you have that volume. And then you add some more gas in, and then the volume increases to 6.48. Okay? So at this volume, your more is this much. So then how do you find out how much gas you added? You subtract the find that N2 with the initial. So more added equals N2 minus N1. So that equals 0.314 minus 0.225. So whatever number you guess, you just, so that's what the answer. Right, so let's do this last CRE, then we'll do the lab. Okay, now as I said, even though you probably get the pattern, you see the what law you use. Because I probably do practice. Just think about it like from the scratch. So what law you use? Should I use Boyle's, should I use Charles, or Avogadro's, or even the ideal gas law? How do you get a C? How did you get a C? Which law did you use?
The one you just did.
Well, the one we did is Avogadro's?
Yeah.
Okay, Avogadro's?
So you do 2.81 times 6.621 divided by 0.1.
Okay, so that is the one set. And then the other one is you can, if you start with that, that's good. 281, that's the volume. You put that on the top, right? And then the weight we don't know. But the N2 you know. Very good. Okay. So what I think what Andy said is you have that. So in the last in the examples I use N1 over V1 equals N2 over V2. Right? So here. This CRE, I don't just reverse it, I just V1 over N1 equals V2 over N2. That's what the actually said, right? And so you see this will be one, so this is one set. So we will call this is our N1. So we'll see N1 equals 0.1 to 0 more, and V1 equals 2.81 L, right? And then we will have N2 equals 0.621 more. Very good, very good, very good. And so you substitute and that just make like a two techniques, you do that, and you Alright, so today's lab, let me just see a little bit about today's lab, okay? You skip like a couple steps. let's see, consider that. So consider that, you don't have to boil. You don't need to boil water. So we'll keep one step. Skip one step. Okay? And another point I want to tell you is we do the acid-base titration, and our base is NaOH, that is common base. Okay? Our acid is not very common called KHP. Okay? Now this P is not phosphorus. This is the abbreviation. This P is standing for that P is standing for the phosphate. Right? So when you say this KHP, so this equals KH. So that the phosphorus, the phosphorus is not here. This P is a C, let me see what number, C8, and H4, and O4. Okay? So this is the formula for our acid. It's very, very like fancy, like organic acid. But you don't have to know like the real structure. This together has the molar mass equals 204.2 grams per mole. Right? So the common mistake, if you don't know that it's for the phosphate, you will take the P like molar mass will know. Right? So then for both part A, part B, just take this acid and take the same base to the titration. Right? For part A, you have the pure. Okay? So pure in part A, you have the KHP, okay? With the pure. That means you have the chemical pure, 99.99%. And then in part B, you will have those different examples. So I think our percent in part B. In part B, we have some like 20%, or we do like 65%. So you don't have the pure KHP. But your egg is still KHP. Some other is starch or something. Or maybe type of salt. So you want to find out, your purpose is to find out how much KHP, what is the percentage of KHP from part B. Alright, so I think that's probably a very easy lab. I think probably by the